Optical lenses are such a fundamental component in a variety of applications because of their ability to control and manipulate the light specific to the application they're going to be used in. One of the applications optical lenses are used in are imaging systems, like the camera we're using now, where light is collected and focused onto the sensor. Optical lenses are also used in laser systems, such as CO2 lasers, to make sure that we can do laser cutting, focus the light to a very precise point to get real precision cutting in a system. The main types of optical lenses that customers might see are spherical lenses, where you may have plano-concave or convex, biconcave or convex lenses, but then you can start getting more complex lenses like Fresnel lenses, or achromatic and aspheric lenses, which are then actually used to reduce aberrations within a system. Different optical lenses are used within systems for different reasons. So you might use a convex lens to actually focus the light onto a sensor, onto another optical component. You might use a concave lens to diverge the lens and spread out the beam to magnify. Or you might use a more specialized lens, such as an aspheric lens or an achromatic lens, to get accurate imaging, which you may not see if you use just a spherical lens. Sometimes aberrations are introduced within a system, especially when you're using a spherical lens, because you're creating different focus points, either due to the shape of the lens or due to how different wavelengths go through the lens. It can go through at different speeds. So at this point, you might use a different type of lens type, such as an aspheric lens can control the spherical aberration. You can do the same by using multiple spherical lenses, but at that point you're going to start losing efficiency. It becomes bulky, which also then will introduce more costs as well, because you're having multiple elements. So you'd use an aspheric lens where you might actually need only one element to do the same thing that you might use 4 or 5 spherical elements. So a normal spherical lens has a spherical profile. You can make a sphere from the lens, whilst an aspheric lens has a different type of surface profile, an aspheric surface profile. And this means that the light going in through the edges and compared to going into the middle will actually focus at the same point, because they're traveling to the same place. Unlike spherical lenses, which focus light to a point, a cylindrical lens will actually focus your light to a line. This is often needed in applications such as laser line scanning. A ball lens, just like its name suggests, is an actual full-on sphere. And the way that works is it means it has a much shorter focal length and back focal length. So they're often used in fibre coupling, because you can put the ball lens between 2 fibres without much of a space between them. They're very efficient in the coupling without losing much of the light between. A half-ball lens is basically used exactly the same way as a ball lens, but is used where space is even more of a requirement. It's important to consider certain optical requirements when specifying an optical lens, such as the material. Is it going to transmit in the waveband you need? The actual dimensions, the focal length, is it going to focus in the right place for your optical system? And then you get to the coating requirements. Does it need an anti-reflective coating to be able to optimise the transmission in the area that you're looking at? Or does it actually need more coatings to make them durable? Does it need a DLC coating, a hydrophobic coating? And then again, dependent on the optical system, such as is it being used in a laser system, at which point the surface quality is critical. You need to specify very high surface quality, such as 2010 scratch dig, as well as laser damage threshold, to make sure that your optical component will actually withstand the laser requirements that it's being used in.
What wavelengths are you using? That informs your material that you can use, and then the materials that you can use, you need size, because certain materials can only be grown to a certain size. So if you have a requirement for a very large lens, certain materials, it's just not feasible to grow a crystal substrate to that size. Durability and environmental requirements. Certain materials are very, very good for transmission of certain wavelength ranges, but are very delicate, potentially hygroscopic, so they will absorb water, and then cloud over, which is not what you want for a lot of systems. So the environment into which it's built is really important. After that, your focal length and things like that are what you're looking for. Potentially the size of the thing that you're putting it into. Certain materials can bend light more than others. So if you had a shorter range or a shorter length requirement for your system, you might go for something like germanium, which has a really high refractive index to bend the light more and allow you to fit your system into a much smaller footprint. Substrate material is really important for your lens performance. First, it informs you what you can actually use in terms of substrate material, your durability requirements for your system, any temperature requirements for your system. Certain lenses just will stop functioning past 100 degrees or thereabouts. Thermal stability, if you've got let's say, a system going up into space, you've got thermal cycling, so the change in temperature will affect how your lens performs. The standard, the one that you should go for first and then decide against otherwise, is BK7. That's a shot material. That is the standard for any visible application. That's the one you should look at first. If you require better image quality, better thermal stability, some kind of fused silica might be better for that. When you move into the UV, past about 180 nanometers, fused silica becomes not really suitable. So you need some kind of crystal fluoride glass, calcium fluoride, lithium fluoride, what have you. They have tighter and tighter durability requirements. So lithium fluoride is really great. It will get you down to near X-ray wavelengths, but it's very delicate. So there's trade-offs there. On the infrared side, you would be going for something like a zinc sulfide or zinc selenide, perhaps silicon, germanium, anything like that. They can allow you to measure from shortwave IR 3 to 5 micron up to thermal imaging 8 to 14, something like that. A coating is going to often impart some variation onto the surface of your lens. So a coating can reduce the image quality because it can warp the surface slightly, but a coating can massively increase the transmission of your lens. For something like BK7, which is a standard glass, you'll lose about 8% of your light going in and out of a lens. A coating can reduce that, depending on how tightly it's constrained, to less than 1%, less than 0.1%, depending on your range. You've also got added durability. Certain materials are very delicate. You can have protective coatings, which can offer some similar properties to an anti-reflective coating in terms of greater transmission, but also significantly better durability. And then you've also got things like hydrophobic or oleophobic coatings. If you've got something that's used for sort of cosmetic applications, you don't want fingerprints on there. So an oleophobic coating, such as on an expensive watch, can often be used, and they can help protect the surface of your optic while also making it look nice as well.